Hello, hello. Well, recently there has been a lot of buzz related to the performance of the LLMs when it comes to mathematics and especially maths Olympiad problems. Um, we're gonna actually try to understand how much of this is true when we apply the LLMs into research level mathematical problems. And I'm not really talking about, let's say, all the well-known hard problems such as the Riemann hypothesis, the Collatz conjecture, not at all, because it is not really how mathematicians approach solving problems. So typically we split the problems into smaller bits and try to prove little theorems that we call lemmas. And today, actually, we're gonna test Grok 4 with a very obscure result that I know for a fact it is true. It is from my area of expertise, which is functional analysis. So if you remember a little bit of, let's say, your calculus maths from college, it is like doing mathematical analysis, but very infinite dimensional objects. So you don't have to worry that you'll not really understand a word from the formulation of the problem. I will guide you through the answers and we will see really how well these LLMs are capable of solving such problems. So a little bit about myself. Well, I'm a professor of mathematics at the Jagiellonian University in Poland and also work as a researcher at the Czech Academy of Sciences. I have, I think, decent track record in pure mathematics and especially in functional analysis. So let's actually try to see how well Grok 4 will let's say attempt to prove a little obscure fact from functional analysis. And personally, I think it will not. It's not going to provide a complete solution. Okay, so let us give it a little bit of context. So let's say we are going to work with Banach spaces. So Banach spaces are like mathematical framework for doing analysis in infinite dimensions. You don't really have to know anything about them. And let's try to be very convincing because I know it is true. It can be, let's even give this information to the model. It can be deduced from a chain of deep results, which is true, that if X is an infinite dimensional Banach space, then the bidual X double star contains a weak star basic sequence, i.e. a sequence that is a weak star Schroeder basis for its weak star closed linear span. So probably it sounds like black magic, and actually I can tell you that, let's say, many professional mathematicians will not really be comfortable with this because mathematics is so huge that if you work in area A, then probably you have a little chance to understand really notions from, let's say, some area B. So don't worry at all. And that's the whole point of this exercise to see how well, let's say, Grok will manage this. So dimension. Let's avoid typos to increase. I'm sure it can actually figure this out, but let's be accurate. So give me a complete proof that would be self-contained of this fact. Verify each step. Tell me where you are using the fact that you work in the bidual rather than the mere dual space. And here is a catch, because if the proof will not use the fact that we are working with what I call here bidual, and if you prove something stronger, that the dual of every Banach space contains such a sequence, that would have solved a major open problem that has 80 years, yes, and it's the separable quotient problem. So I don't think it can be done this way. So let us see what it can offer. Okay, it's thinking. The question involves conventional Banach spaces, right? A weak star shard basis means a sequence where a series converges. In the weak star topology with, well, kind of, yes. Okay, it's looking for some papers. Right. The weak star topology is pointwise convergence. Kind of, yes. If it, okay, exploring. I wonder how long would it take actually to generate some answer. Let's search for proof. Oh, Matt Dawes, I know this guy. Interesting. Very curious what Grok is going to spit out. The proof uses induction. Well, yeah, could be. It could be a valid proof strategy. Well, okay. While it is, let's say, thinking or doing whatever it is doing, I can tell you that I have a feeling that that especially the quality of thinking of Grok when it comes to pure mathematics kind of deteriorated. And I observed this already with Grok 3, where it initially came out. I think it was extremely good, let's say, with solving like a even postgrad level textbook problems in, let's say, functional analysis or any other areas of maths. And then gradually I observed, but this is just my observation. It became kind of less and less accurate. Oh, Antonio Villas, I also know this guy. Okay, so let's see. It's reading some papers. Oh, Manolo Gonzalez, he's my actually quarter. Interesting. I also know the second guy. So, let's say in the maths community, if you work in some area, kind of everyone knows everybody. It's reading some paper that, well, the title doesn't really ring a bell to me, but I'm not sure if this is really on topic. The proof is cut off. What proof? Probably the proof that it was reading. A weak star shard base. Okay, so it repeats the definition. Uh, every element in the weak star closed span has a unique representation. Yes, that's the definition. Um, Interesting. It takes so much time, which is good, right? Because the this result is non-trivial, and I don't think, well, I'm sure it is not written anywhere in the literature. So the paper that could be used to deduce this result is from 2008, and I'm sure that actually all those models have read all such papers because they are freely available on Archive. So if you don't know, Archive is this free repository of preprints. So it is I guess one of the first places for these LLMs to be trained on. So I'm sure it knows the paper. However, it is not really explicit in the paper that you can deduce it. So I don't think it's gonna connect the dots and say, oh, this is how we deduce it. Okay, it's thinking and thinking. Very good. Comparing dual and bidual. Completing the proof. So it's gonna give us the proof. The proof approximates something. Yeah. Later on, we will actually take exactly the same result and we will test it against other models, especially ChatGPT and Gemini. The proof works similarly both for dual and bidual, so hence it must be wrong. I mean, no chance it's gonna provide the proof for the dual space alone. We'll see, because maybe it will self-correct. The proof uses linear system solving for finite spans. Oh, sounds like some generic mumbo jumbo. Oh, it's building weak star bases. Oh dear. Super curious. The weak star. Oh, it's reading some new paper. Weak sequential convergence in the dual of a Banach space. Fair enough. I'm so excited to see the proof. It's not giving up. So once we have the proof, we will ask the model to give us something is coming up, to give us the later code, and then we will actually ask Grok um, to challenge the proof. Okay, so let's just skim through it. Of course, we're not going to find any, well, at this stage, some definite answer, whether it is true or not, but let me at least read the fact that it is using Rosenthal. For every infinite dimensional Banach space E, there is a sequence in E star. Well, that's not a convention, but let's say some people denote it by E prime. So to me, it is E star that tends to zero in the weak star topology, but not in norm. So of course, the first kind of mismatch here, that this theorem is not due to Haskell-Rosenthal. This is the kind of locally celebrated theorem of Josephson-Nissen-Zweig. It is from the 70s, but this is not due to Haskell-Rosenthal. Okay, so now tries to apply it to E being the dual. Okay, but Johnson-Rosenthal selection principle, if Fn is a semi-normalized weak star null sequence, then there is a norm-based sequence. I'm not sure if the formulation is actually correct. And Besaga-Pełczyński selection principle It's a standard result, but it is for basic sequences, but in a different sense. Each step in part one uses separability. Well, we don't really assume separability by orthogonal constructions and combinatorial partitioning in L infinity. Okay, let's do this. Give me complete LaTeX write-up of the proof with all the details explained. So now, I mean, in Grok 4, I think there is... Oh! No, there will be a glitch because you see some of these things, like the code might parse, but so far it is doing well. Okay, we'll see. Kind of, I have a very strong suspicion that it's gonna be wrong because it assumes some property that is called separability that I don't really want to assume because actually under that extra assumption, I think the proof can be derived. And actually the whole point is to not to assume anything, anything extra. Oh dear, triangle, tridiagonal, okay. The bidual, the extensions, okay, fair enough. It reflects on the fact that it has to be in the bidual, so let's copy this and paste to another window. So I was given this proof, which I highly doubt. Challenge it and find gaps. Say whether it is correct or not. Oh, this is Grok 3, so let's switch to Grok 4 because today we're testing Grok 4. Oh, and this in Grok 4 you don't really have this think or do whatever, it figures it out automatically. All right, okie doke, let's see what happens. The LaTeX document presents a proof that every infinite-dimensional Banach space has a bidual with a weak star basic sequence. Well, the wording is not perfect, but it is actually what we are going to. But it's more or less correct. Rosenthal's theorem. This is of course not due to him. The proof seems messy, yes. Adapting Rosenthal's theorem on L1 embeddings. So I think it kind of merged two results. One is this theorem, this Josephson-Nissen-Spike theorem, and there is another result by Haskell-Rosenthal that is kind of related. Let's see. Checking in. The theorem claims every infinite Banach space has a weak basis in its weak topology, but this is not what we are asking, and this is, for experts, this is obviously true. I know that for you it could be very confusing because I'm talking about, or at least I'm saying words or like weak star basis, Banach space, but actually that's the whole point. Not to, let's say, solve, let's say, Maths Olympics problems where the formulation is kind of understandable by pretty much any high school student. Here you have like a real mathematical problem that, well, for the purpose of this video could be deemed open, yeah, and see how well these models actually can cope with that. Weak star null Don't. Oh, I didn't read. The prove wrongly claims. Let's see. Oh, and I was just googling the answer. I'm afraid you're not gonna find it, mate. Um, if yn is a norm basic sequence, blah blah. Uh, Interesting. Oh, seems that it's found the error. Yes. Oh, yeah. Johnson-Rosenthal selection principle. Actually, I would like to say hi to Bill Johnson. Actually, I'll be attending his 80th birthday anniversary conference in November this year in Oregon. So hi, Bill. um, User proofs try to make the sequence non-basic first, but that's where the error occurred. All right, okie doke. The proof contains significant gaps and errors, yes, making it incorrect as presented, yes. However, the theorem itself, well, it's true, yes, I know it is true. The proof claims that the sequence Fn is weak star, so it is weak, so it is, sorry, it is weak star null in X double star, but it doesn't mean it is weak star null, whatever it means for you in double star. Yes, 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 yes. The Saga-Pociński selection principle requires a semi-normalized weak null sequence to extract a norm-basic sequence, but we're not looking for norm-basic sequences. They're not going to help us. Okay, misalignment with theirs. Did it really identify the right theorem? No, I don't think it. Well, at least it reflected that it is kind of not the not the proper formulation as I mentioned. Is the theorem correct? Let's read it. Yes, the theorem is correct. Every infinite-dimensional Banach space has an infinite-dimensional dual. So the bidual contains a semi-normalized weak star null sequence. Well, yes, it does, but it doesn't prove anything. The Johnson-Rosenthal selection principle then guarantees the weak star basic sequence with. No, it does not. It is. No, 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 no. Hold on. It is not that easy. Oh, right. So, of course, we could now iterate it many, many times and say, oh, now correct it. But I think that this flaw is so fundamental that we would need it would need to kind of invent the proof anew. So you can play with that and let me know. Maybe you have a your own proof if you're a mathematician working in this area. That would be interesting to see. But for today, well, I think it is a no. So sorry, Grok, you need to learn more functional analysis. And thanks for watching.